Good morning, everyone. So first of all, I thank the organizers for inviting me to this wonderful conference. Uh, so today I'll be talking about quantum technology with ultra-cold Rydberg atoms. So the outline of my talk, I'll give a basic introduction to quantum technologies with Rydberg atoms in general. And then I'll talk about a few measurements and interesting results which we have got in our lab in the past few years, like the transition frequency measurements of highly excited Rydberg states. And we had this very interesting result on Doppler enhanced quantum magnetometry with Rydberg atoms and quantum sensing of microwave field with Rydberg atoms. And last year we had observed the effect of interaction in Ottertown splitting in cold Rydberg atoms. And finally, I'll give a future perspective on scalable quantum network and quantum sensing with optical tweezer arrays with cold Rydberg atoms. So quantum technology is the acquisition, storage, transmission, and processing of information using quantum sensors, processors, and transmitters. So quantum technology can be broadly divided into 4 different regimes. One is quantum computation, quantum sensing and metrology, quantum simulation, and quantum communication. So I'll show you that with a versatile platform of Rydberg atoms, we could explore all these different regimes of quantum technology. So Rydberg atoms are giant atoms with the electron excited to very, very highly excited state. And this gives it a very giant size. And so they are also called the giants of the atomic world. So Rydberg atoms were discovered way back in 1888 by Johannes Rydberg. And this played a very important role in the birth of quantum mechanics. So because the electron is excited to very highly excited state, the atoms acquire a very large dipole moment, and hence it has some exaggerated properties. For example, it has a very large size, and because of this large size, it is ideal for exploring mesoscopic quantum regime. Also, it has very large radiative lifetime, which goes as n cube, where n is the principal quantum number to which the electron is excited. And this gives long coherence time for quantum technology applications. Also, a very important property of Rydberg atoms is its very large polarizability, which goes as n to the power 7. And this makes Rydberg atoms extremely sensitive to small DC or AC electric fields, and hence it's so promising for quantum sensing and metrology. And finally, we have another very important property of Rydberg atoms is that they're very strongly interacting. That means it has large dipole-dipole interaction, which goes as n to the power 4, and the van der Waals interaction goes as n to the power 11. So you seldom see such strong dependence on the principal quantum number of any properties of atoms. So this very strong interatomic interaction between Rydberg atoms makes it a very promising platform for various applications such as quantum computation, because a strong interaction enables quantum entanglement via Rydberg blockade to realize fast quantum gates. We can do quantum simulation of condensed matter systems, and we can use Rydberg atoms as a very deterministic single photon source for quantum communications. So here you could see we could explore all the different regimes of quantum technology using Rydberg atoms. So let me give you a quick comparison, especially for the students. So how does Rydberg atoms compare with atoms at lowly excited state? So you could see the size of low excited states are like angstrom, but Rydberg atoms can be as large as microns in size, like the size of a bacteria. It has, for other atoms, the lifetimes are like in nanoseconds, but in Rydberg atoms, you can have very long lifetime, like 100 microsecond, and for some special circular states, it can be as large as 1 second. So it can give very long coherence time to Rydberg atoms. And the van der Waals interaction, the range is very small for other atoms, like 1 nanometer, but with the same interaction strength, the range is long range for Rydberg atoms, like at 10 micrometers. The level spacing in other atoms is like in optical frequencies, but in Rydberg atoms is there in like in radio frequency or microwave frequency, and hence they're very extremely nice quantum sensors for a wide range of electromagnetic radiation with a very wide range of frequency, right from terahertz to microwave to radio frequency. So I'll like to describe this phenomena, which is at the heart of making Rydberg atoms so promising for quantum computation, which is called the Rydberg blockade. So as I had mentioned, Rydberg atoms are very strongly interacting. If you have one atom excited to the Rydberg state, and if you bring another atom closer together, because of the strong interaction, there's an energy level shift of the other atom, and the laser which is exciting one atom to the Rydberg state cannot excite the other because of the energy level shift, and vice versa. So you can see that there's a correlation which is formed between the two atoms, and which leads to quantum entanglement of the atoms. And so this is called Rydberg blockade effect, because the excitation to the Rydberg state of one atom blocks the excitation of the other. So how do we detect the atoms in the Rydberg state? So we use a very interesting quantum optics phenomena called Rydberg electromagnetically induced transparency. So here you could see that we take a 3-level system, which is here in this case is a ladder type of system. So if you have just this 2-level atom and we scan the laser beam across the resonance, we'll get just this absorption profile. But if we have another transition, which makes it a 3-level system, there is a destructive quantum interference between the transition probabilities of this 2 transition, which leads to complete cancellation of the absorption. So this is what is called a electromagnetically induced transparency, and we use the signal to detect atoms in the Rydberg state. So here you could see the Rydberg electromagnetically induced transparency, or EIT signal here, which we have used to detect atoms in the Rydberg state. Now, when we had started the experiment, like we wanted to go to as high Rydberg state as possible, because higher we go in principal quantum number, more interesting the properties become. But at the time, the transition frequencies of, so we do a 2-photon transition to go to the Rydberg state, which is like ground to the intermediate state, and from the intermediate to the very highly excited Rydberg state. So these transition frequencies were only known till n equal to 55, but we wanted to go way beyond n equal to 100. So we did a comprehensive measurement of the transition frequencies all the way to 125, n equal to 125. So this enabled, further exploring the very highly excited Rydberg states in our experiment. So here you could see we could measure the fine structure splitting accurately from our measurements. And here you could see the final results of our measurements. So these are actually points which has become almost continuous, because as you go higher in principal quantum number, the level spacing becomes smaller and smaller, and that's why it becomes almost like continuous. And with that, we could also get very accurate values of quantum defect, which characterizes the deviation of the Rydberg atoms from the hydrogen-like behavior. So now I'll talk about another very interesting result which we got by accident in our experiment. So our experiments are always so full of surprises. So when we were doing our measurements of the transition frequency, we got another signal which was a bit broad. So this is the Rydberg EIT signal which we were expecting, but there was another broad signal, and we were surprised why it was coming. And then we were realizing that this laser beam was very highly intense. So there was a back reflection from the glass cell. So generally, we make these 2 laser beams counter propagating to compensate for the Doppler shift. Though we cannot compensate it fully because the wavelengths are completely different, so there's a Doppler mismatch, but we try to compensate as much as possible. But this one, because it was co-propagating, the Doppler shift was not compensated, and that's why we got a broader signal. Now, to understand it better, we put a magnetic field using a solenoid, and to our surprise, we found that this other signal had a Zeeman splitting, or the response to the magnetic field, an order of magnitude larger as compared to the response to the magnetic field of the conventional Rydberg AIT signal. So this was a very surprising result. Uh, so we collaborated with Shobhan Datta, who was here on Monday. So he's part of this conference. So we did a theoretical modeling in collaboration with him. And so the modeling was based on Lindbergh master equation under Born-Markov approximation. And we could get a very nice theoretical modeling results, which was matching very well with our experiments for both the circular polarization as well as the linear polarization. So why it's a big deal? Because high sensitivity magnetometry has a lot of very important applications, right from navigation to geophysical and mineral exploration to archaeology, security and space exploration, and very importantly, defense application as well as medical research. So I go to the next part of my talk where I talk about very important project in my lab, which is quantum sensing of microwave and radio frequency fields with Rydberg atoms. So as I had explained that we were using a 3-level system to observe the Rydberg AIT signal. Now we can transform this 3-level system to a 4-level system using a microwave radio frequency or a terahertz field. So as I had said, that the difference between the Rydberg states have the difference lies in either microwave, radio frequency, or terahertz, depends on which principal quantum number we are choosing. So we coupled the two Rydberg state using a microwave field, and we could see Ortler-Town splitting because of the effect of the microwave field, and which makes this Rydberg atoms a very nice quantum sensor for a wide range of electromagnetic radiation in the microwave regime as well as RF regime. So when we have a low microwave power, you could see that it's hardly, it's broadening slightly, and we could see a very nice Ortler-Town splitting when we get a larger microwave power. So this kind of signal we can use for quantum sensing with Rydberg atoms. So why? So generally we have the conventional sensors for sensing electromagnetic radiation. So why go for Rydberg atom sensor? So there are many advantages which Rydberg atom sensors has over conventional sensor. For example, for every frequency range, for sensing each of this frequency range, you have to make a different set of classical sensors or antenna. But in Rydberg atoms, the single Rydberg atom, depending on its energy levels, it can sense a wide range of electromagnetic frequencies, right from radio frequency, microwave to terahertz. And also a very important difference is that the classical sensors are mostly, they are man-made sensors, and they are prone to manufacturing defects, and they are not same everywhere. So they depend on how they are manufactured, and the accuracy of how precisely they can probe, it depends on how accurately they are calibrated. But Rydberg atoms are self-calibrating. They are the same everywhere in the universe. So they don't rely on accurate calibration. So that's why Rydberg atoms are very promising and superior quantum sensor for electromagnetic radiation. And of course, Rydberg atoms have very high spatial resolution. So this is a picture of our quantum sensing experiment at Raman Research Institute. So we have a Faraday cage with microwave absorbers so that we prevent any standing wave to be formed, and we detect the microwave radiation with very high accuracy. So till now we have successfully detected a power of microwave radiation as low as minus 50 dBm, but our target is to make it as precise and as highly sensitive as possible to go to as low as minus 50 dBm power detection. So we have explored both amplitude and frequency modulation with the microwave field. And here you could see that with amplitude modulation, we could, so this is without amplitude modulation, we could see this avoided crossing, and this is with amplitude modulation. So we have explored all these parameters. And of course, Rydberg atomic sensor has a very wide range of very important applications, right from satellite communications to radar sensing, to navigation without GPS in atomic clocks. So there are new results on Rydberg atomic clocks, as well as gravity detection, as well as radio astronomy. So now I come to the next part of the talk, which is the main focus of our experiment, is to have Rydberg excitation in ultra cold atoms. So this is our experimental setup where we have the cold atoms, where we do the Rydberg excitation. So we have two complementary detection systems. One is the camera as well as a single photon detection module, where we can have the very efficient detection with very good timing resolution of like 5 nanoseconds. So this enabled us to observe Rydberg excitation in cold atoms. So we use the cooling laser of the magneto-optical trap to excite from the ground state to the intermediate state, and then we use the Rydberg laser to probe this excitation. So probe this. So when we have this very intense cooling laser, it causes a AC Stark shift and causes the Ortler-Town splitting, and we use the Rydberg laser to probe this Ortler-Town splitting, as here you can see. So here you can see the signal for Ortler-Town splitting in the cold Rydberg atoms. And we observed a very interesting phenomena that as we go to higher principal quantum number, because of the increase in the interatomic interaction, there was a broadening of this Ortler-Town splitting signal. And as we went above principal quantum number n equal to 100, we saw a complete distortion of this Ortler-Town splitting signal because of very strong interaction between the Rydberg atoms. So we did theoretical modeling in collaboration with Rejish Nath, who is one of the organizers of this conference. And here you could see a very beautiful matching of the theoretical modeling with our experimental measurements. So here's our final result. We could see a drastic increase in this broadening and the Ortler-Town splitting as we cross the principal quantum number n equal to 100, signifying extremely strong interaction between the Rydberg atoms. So here are a few publications which we had in the last few years from our Rydberg atom experiment. So since we want to go to higher and higher Rydberg states, which has lower and lower splitting between the Rydberg levels, so we would like to have a very stable locking of these two Rydberg excitation lasers to a cavity, and hence we have locked these two lasers, Rydberg excitation lasers, to a cavity of high finesse cavity. So here you could see we could reduce the line width of the lasers from 500 or few hundred kilohertz, like 600 to 500 kilohertz, all the way to a few tens or 30 kilohertz line width. And we are working towards reducing to as low as 1 kilohertz line width. So this will give a long coherence time in our system for our Rydberg excitation of cold atoms. So we could also observe a very stable Ortler-Town splitting signal with increased fraction of the atoms in the Rydberg state when we lock these lasers to the reference cavity. And here you could see the difference. So this is without the locking, and it's very noisy. So when we lock the laser to this cavity, we could get an ultra stable laser, which was stable for a long time. So this enables us to address very highly excited Rydberg state with long-term stability in the system. So the next step in our experiment is to trap individual atoms in optical tweezer. So we have high numerical aperture lenses inside our vacuum chamber, which focuses the optical tweezer laser beam to very small focal spot of 1 micron. So this very small focal spot is required to ensure that either there is 0 or 1 atom in the optical tweezer. So if there are more atoms, if there are more than 1 atom, both will undergo inelastic collisions due to light-assisted inelastic collisions, and both of them will go out of the trap. So this very small focal spot ensures single atom trapping in the optical tweezer. So we have already successfully made an optical tweezer with sub-micron focal spot, which enables single atom trapping. So we have made several patterns for of the tweezer array where we can trap the atoms we're using a spatial light modulator. So we could program it as we want, and we have also written the name of our lab, Coral, which stands for Quantum Optics with Rydberg Atom Lab, using the array of optical tweezers. So we can arrange the atoms in as many patterns as we want. So we already have atoms in the optical tweezer, but they're not single atom at the moment. They're large number of atoms because we want to optimize our imaging system to look at very, very small number of atoms. So right now, it's a larger optical tweezer with 5-micron focal spot. So you could see the lifetime of the trap. And here we could see the atoms also with the single photon counting module. And soon after we optimize our imaging system, we'll go to 1-micron tweezer for single atom trapping. So let me come to the future perspective. What our plan are in our experiment with the optical tweezer array with Rydberg atoms. So the idea is to have individual atoms trapped in an array of optical tweezer and then excite them to the Rydberg state and create quantum entanglement between them using Rydberg blockade and create a large quantum network of this Rydberg atomic qubits. So we are also building a new generation of experiment with glass cell rather than a vacuum chamber, where we'll be having the imaging system outside the glass cell for better high resolution imaging of this array of optical tweezers. And we will be also doing quantum sensing with individual Rydberg atoms. So we all know that in a microscopic regime, which mostly follows single particle physics, and in general, in a macroscopic regime, there are a lot of interaction. It follows many body physics. But the regime in between is very interesting, which is the mesoscopic regime. And Rydberg atoms, because of its large size, is just in the perfect, it's just perfect to explore this mesoscopic regime. So the idea is to have an atom by atom assembly to go from a microscopic regime to explore this mesoscopic regime and then explore the scalability to form a macroscopic 1D or 2D array of this quantum network of Rydberg atomic qubits. So Rydberg atoms in an array of optical tweezer is also very promising for quantum simulation of many body physics. For example, if we have this atoms arranged in a triangular or a square array and use the Rydberg blockade effect, we could do quantum simulation of antiferromagnetic ordering and address open problems in quantum magnetism. So also, because of my experience in Anderson localization and disordered potential, I would like to combine this long-range interaction in Rydberg atoms with disordered potentials and look for new quantum phases in this many-body localized phase. So another very interesting direction to explore in such kind of system is spin glasses, which has not been explored very much using Rydberg atoms. So spin glasses are magnets with random frustration. So it combines random coupling with frustration. So in a triangular lattice, we could have like ferromagnetic or antiferromagnetic ordering, and we could realize spin frustration in such a system. And spin glasses, they are like described by various kinds of models like Edwards-Anderson model or Sherrington-Kirkpatrick model. So there are still, there are open problems in such kind of system. There has been a recent theoretical prediction that programmable amorphous Rydberg atom arrays are promising for experimental realization of quantum spin glasses. So one could observe a quantum phase transition from a paramagnetic to spin glass phase. So this is one direction we would like to explore in our system. So as I had mentioned that Rydberg atoms are, has extremely high polarizability for quantum sensing and metrology. So we would like to do quantum sensing with individual atoms where it would be very accurate because there won't be any ensemble average as in a cloud of atoms. So we could beat the standard quantum limit via quantum tricks such as squeeze states and reach the Heisenberg limit as mentioned in the talk by Anna Maria on Monday. So this is one direction we would like to explore in our experiment. So here is the schematic for the setup for quantum sensing with individual Rydberg atoms. So as I had explained, described in my talk that Rydberg atoms are a very versatile platform for exploring various regimes of quantum technology, such as quantum computation, quantum sensing and metrology, quantum simulation of many-body physics, but there are more. We could also use Rydberg atoms as a futuristic dipole antenna for observational astronomy, emulation of complex solid-state system, and we could also explore ultra-fast quantum dynamics. So this is one of the very important slides which shows the people who contributed to the work I've shown in today's talk. So I have Yashika as PhD student who is here working on quantum computation. Aishwarya is working on quantum sensing. And Shilpa is doing postdoc in the group of Christian Gross in Tübingen. Shobhan has just submitted his thesis, and they were intern students who also contributed a lot to our experiment. And I have very strong theory support from Shobhan Datta, who is in-house theorist in RRI, and Rejish Nath for our cold Rydberg atoms. So I come to the end of my talk. So I summarize what I described. So I gave an introduction to quantum technology with Rydberg atoms. I described our results on quantum enhanced quantum magnetometry with Rydberg atoms. I described our effect of very strong interatomic interactions on cold Rydberg atoms in the Otler-Town splitting signal. I described our quantum sensing experiments at RRI for microwave and radio frequency fields. And then I gave future perspective on quantum information and quantum sensing, as well as quantum simulation of many-body physics with ultra-cold Rydberg atoms. Thanks for your kind attention.
Sanjukta, thanks for finishing early. There are time for a lot of questions, so we can take some. Yes, please.
Very nice talk, very nice, impressive. So for the sensing, of electrical sensing, do you think there could be any gain of using entangled atoms? I mean, you were mentioning single Rydberg, yes, but is there any prospect for using?
Yeah, so as I was saying that we could use squeezing, for using the correlation to have squeezing in the system so that we could, the parameter which we want more precision in, so we could have it like using squeeze state, we can measure it more precisely.
So this is in the direction of the experiment?
Yes.
Or first you start with the one atom and then, is there a roadmap or?
Yes, so we are still, in the planning stage of that experiment. So we will be certainly using, squeezing in.
And for the squeezing, just a little bit more detail. You are
we'll be using interaction.
for dressing or direct Rydberg interaction?
Yeah, we will be using Rydberg interaction.
Direct.
Yes.
More questions?
Similar for your metrology plans, because your Rydberg arrays are extended, Are you thinking about measuring any kind of extended quantities in the metrology experiments you're planning, instead of just scalar quantities?
Yeah, I mean, in metrology, of course, now there are proposals that Rydberg atoms can be also very useful for Rydberg atomic clocks. So we would also explore that direction, whether it can be used for Rydberg atomic clocks.
Okay, more questions? Well, if not, let's thank the speaker for a very nice talk. Okay, so the next talk is by Professor Abhishek Dhar from ICTS.